right, let's go ahead and talk about some right triangle trigonometry. You probably have referred to this prior to this course if you're looking at this from a pre-calculus point of view, and you've used a process that we would often refer to as SohCahToa for this. So that's the topic, and let's take a look. All right, boy, hit you with a biggie right here, and these are identities that we expect you to know at this time, and it looks like a lot, and I'm going to try to convince you that maybe it's not as much as we might think. By this time, I would like to suggest that our reciprocal identities, we're comfortable with those. And in fact, you really, if you know these, you know those. If sine is a reciprocal of cosecant, cosecant is obviously the reciprocal of sine, but I suspect that we already know these at this point. Cofunction identities, this might be a new one, and it looks like, oh, 6 things we have to memorize, but this is a one-size-fits-all. Cofunction, sine, cosine, secant, cosecant, tangent, cotangent, cosine, sine, cosecant, secant. That's why they're called cofunctions. And if you take a look at these, I would suggest if we had a function, a new trig function called star, if we had star, then the rule for star of theta would be that it equals costar of pi on 2, or 90 degrees, minus theta. It is a one-size-fits-all rule right there. So if you haven't seen these ones, there's not 6 things to know there. There's one concept to understand. Okay, I would suggest that by this time you have used this guy extensively. We're going to talk about this a little bit on the next slide, where this comes from. You may have referenced these before, but perhaps you don't use these. We tend to specialize in sine and cosine. However, later on in this chapter, you're going to see I am most definitely not a slave to going to sine and cosine. The reason we go to sine and cosine is that it's so convenient because we have this identity. But if I'm given an expression or an equation or an identity in terms of just tangents and secants, I'm staying there and using this. Cotangents, cosecants, I'm not converting those to sines and cosines. So I give no preferential treatment to sines and cosines unless we get a whole mismatch of trig expressions in one function, or one expression. You'll see that a little bit later on. So next slide, we're going to talk about why these are what they are. Okay, even odd identities. If we just look at this, this is not one size fits all. Here's the deal on these. If we understand what the graphs look like on these, we've got it made. Hopefully by this time we know, I'll draw a quick little sketch here, that the graph of sine of x looks something like this. And if we interpret this the way we should interpret this, that would be the height of sine to the left. Well, sine to the left a certain distance gives me the opposite of what I get with sine to the right. And that's what this says. Sine to the left is the opposite of sine to the right. So that works out great. And obviously, if sine works that way and cosecant is reciprocal of sine, cosecant works that way as well. That is an odd function rule. The height to the left is the opposite of the height to the right. Or we can spin around the origin 180 degrees and get the same graph. That is an odd function. So let's talk about tangent. If you don't recall what the tangent of what the graph of tangent of x looks like, trust me, that will be one you will know. So a quick little sketch over here of what the graph of tangent looks like. Tangent is nicely confined between asymptotes, negative pi over 2, pi over 2. That's sort of irrelevant for what we're talking about right now. One period of tangent looks like this. And once again, we see that the height to the right gives us the opposite of the height to the left. The height to the left is the opposite of the height to the right. And you say, oh, why not just pull the negative out? Well, let's take a look at cosine graph. The cosine graph, get rid of this. Cosine graph, if I squeeze that guy in here, you may recall, starts up here, looks a lot like the graph of sine, as we might expect. that looks like this. And now we note that the height to the left is the same as the height to the right. Or if I go further, the height to the left is the same as the height to the right. Therefore, we get, if you're just looking at this without noticing that, you may think, oh, I forgot something here, forgot the negative. Nope, the height to the left is the same as the height to the right. Cosine is an even function. It folds over the y-axis onto itself. That's an even function. So there's our even odds. Trust me on this one. Once we start talking about graphs, these are going to make perfect sense to you. Okay, and then finally, quotient identities. I would suggest you have used these before. You know these. There are truthfully 4 more quotient identities. We could get a quotient identity for sine and cosine and secant and cosecant, but we typically migrate by turning things into sines and cosines. So you'll see a little bit of that a little later on. So there's a lot there. You may want to take a look at that. You may want to come back and refer to this portion of the video. Maybe take a screen, capture screen, shift print screen, and print this one off if you don't have it. Or if you're on our website, this is definitely, this appears right in the beginning of our website on section 4.3. All right, the reasons behind Pythagorean identities. Okay, let's go ahead and just draw a right triangle since we're talking about Pythagoreans. If I call this theta, you might refer to this as the opposite. I'm going to refer to this side as y. You might refer to this as the adjacent. I'm going to refer to this as x. And you might refer to this as the hypotenuse. I'm going to refer to this as r. So Pythagorean, what do we know? We know that x squared plus y squared equals r squared. But trig functions are ratios of x, y, and r, or opposites, hypotenuses, and adjacents in SohCahToa land. So I'm just going to divide by, what if we divide everything by r squared? If I do that, of course, r squared on r squared becomes 1, but x on r is adjacent on hypotenuse. That is cosine. So x squared on r squared is cosine squared of angle theta. Plus y on r, opposite hypotenuse. Opposite on hypotenuse is sine. There's a Pythagorean identity. How about this? How about we go back to x squared plus y squared equals r squared, and we divide by, for whatever reason, x squared everywhere, both sides. Here I get clearly x squared on x squared 1 plus y on x. Y on x. Opposite, adjacent. That is tangent. So tangent squared of theta equals r on x. Hypotenuse on adjacent. Well, adjacent on hypotenuse, I know is cosine. Reciprocal of cosine, secant. This is secant squared of theta. That's one of our Pythagorean identities. How about the third option for me? X squared plus y squared equals r squared. What if I divided everything by y squared? I can do that. I know y is a distance here. X on y. X on y. That's adjacent opposite. Well, opposite adjacent is tangent. So the reciprocal of that, cotangent squared of theta plus y squared on y squared 1 equals r, or hypotenuse on y opposite. Hypotenuse opposite. Well, SohCahToa, S-O-H. Opposite on hypotenuse is sine. I need reciprocal of sine. Cosecant squared theta. Now, I would suggest this. You are never very far removed from knowing all of these by this process. If you forget and you're dealing with tangents and secants, it's not hard to get here. I would also suggest, though, that these pretty much take on the same form. The tangent, cotangent part gets squared and has 1 added to it. And the cosecant, secant part gets squared and it's isolated on one side of the equal sign. Cofunction goes with cofunction. Non-cofunction goes with non-cofunction. probably be worth your time. You know how I feel about memorizing. It's nice to understand where they come from, but I suspect you'll see enough of these, you'll get this down. This will be kind of like, this will be like shoe tying. You didn't think about tying your shoes this morning. You're not going to have to think about 1 plus tangent squared equals secant squared soon. Okay, some applications of these. Find the exact value of the 6 trig functions. So the ones that clearly I can find right away are based on opposite and hypotenuse, or what I would refer to as y and r. I would refer to this as x, I think for obvious reasons. We go over x, up y, and we're rotating around the origin, if we would consider that the origin, along a radius of 13 here. So opposite, hypotenuse, y on r, sine is 5 on 13. And if I've got sine 5 on 13, I've got cosine, or cosecant, excuse me, 13 on 5, reciprocal. Okay, now, cosine includes x, or adjacent. Tangent includes it. I need my x value here. So I'm going to go through Pythagorean process. You might recognize this as a Pythagorean triple, and that's great. But we could say 13 squared equals x squared plus 5 squared. 169 equals x squared plus 25. X squared is 144 when I subtract 25, so x wants to be algebraically plus or minus 12, but minus 12 makes no sense. Not in this problem. So cosine, if this side is 12 now, cosine x on r, or adjacent hypotenuse, 12 on 13, making secant, reciprocal, 13/12. Tangent, y on x, or opposite adjacent, 5 on 12, making cotangent 12 on 5. So nice Pythagorean family there. You may have come up with that without going through this process. You may have recognized the 13, 5, 12. Okay, but Pythagorean triples aren't going to get us through all of these. Let's take a look at a triangle where cosecant of theta is 17 on 4. So we're supposed to find the other trig functions. Well, cosecant 17 on 4 tells me that sine is 4 on 17. That one's a breeze. Now, if sine 14 on 7, if I go ahead and draw my triangle here, I'm not trying to draw this to scale. You certainly could try to. Sine is y on r, or opposite on hypotenuse, 4 on 17. So if I refer to this side as x, I can say 17 squared equals x squared plus 4 squared, or 289 is x squared plus 16, or x squared equals 273. X wants to be the positive version of this because it's a distance. Square root 273 that I do not believe breaks down for us. 9 doesn't divide it, 25 doesn't, 49 doesn't. Clearly even squares don't divide it. So that is x. So cosine, if this is root 273, cosine, to get cosine, I want x on r, root 273 on 17. Root 273 on 17 means that secant is 17 on root 273. I personally am fine with that. I expect everyone watching this by this time has some algebra background and knows that we could rationalize the denominator and make that 17 root 23 on 273. And tangent? Tangent is y on x, or opposite on adjacent, 4 on root 273. Now, if you're forced to rationalize that, that's great, but I would do this first and then go through the rationalizing process and make that 4 root 273 on 273. It sure makes the reciprocation a lot easier in this case. So, nothing to it. Back to geometry days. Okay, sketch a right triangle with acute angle theta. Find the value of theta in degrees and radians. Ooh, this guy looks familiar. This looks like it has been rationalized. Let's take a look. What if I was to multiply this by, let's just go times square root of 3 on square root of 3. I would get 3 on 3 root 3, or 1 on root 3. And if you're familiar with our 30, 60, 90s and 45, 45, 90s, those are good values. Cotangent. I'm not going to try to draw this to scale. We'll think our way through this. Here's theta. Cotangent, reciprocal of tangent. Tangent, opposite on adjacent. So adjacent on opposite, or tangent y on x. This wants to be x on y. So x1, y root 3. And you could go through Pythagorean theorem, but this is 2. And hopefully we recognize that as a 30, 60, 90 triangle. It's just what is theta? I didn't draw it to scale. I think that sometimes is a dangerous proposition. Well, theta has to be 30 or 60, but square root of 3 is bigger than 1. So theta, the angle opposite root 3, must be 60 degrees. And that, of course, is 1/3 of the way to 180. So pi on 3. Use the given function values to determine the values of the indicated trig functions. All right. Well, if they tell me sine of 30, I'm hoping somewhere they're asking me about cosecant of 30. Reciprocal. If they tell me tangent of 30, somewhere I hope they're asking for cotangent of 30. They are. This is rationalized version of 1 on root 3. So cotangent of 30 is root 3 on 1. Cotangent of 60. What do we note? We note those add up to 90. And earlier we talked about cofunction rule that says if we had a trig function called star of x would be equal to co-star of 90 degrees, or pi on 2 minus x. So tangent of 30 is equal to cotangent of 90 minus 30. Or tangent of 30 is equal to cotangent of 60. Cotangent of 60 must be 1 on root 3. Or if you like, root 3 on 3. How about cosine of 30 though? Wow, this would be easy if we were drawing the triangle, but it is not their intent to have us draw the triangle. But what do we know about cosine, sine, and tangent? They live together in this quotient identity that says tangent of 30 degrees equals sine of 30 degrees on cosine of 30 degrees. Or tangent of 30, I'm going to call it 1 on root 3, equals sine of 30, 1/2 on cosine of 30. If I cross multiply, I get cosine of 30, I don't know why I put that there, cosine of 30 degrees equals square root of 3 times 1/2 root 3 on 2. So cosine of 30, root 3 on 2. Probably easier just to draw the triangle, but they were really hoping for us to get this just through identity work. All right, proofs. I'm very picky about proofs. Proofs, we have to show detailed steps. I may not, for instance, divide both sides of this equation by cosine, no matter how tempting that is. We don't know if these are equal to until they've been proven. And the reason that I can do, if I'm solving an equation, 2x equals 12, I can divide both sides by 2 because we are told those are in fact equal. The division property says if two things are equal, we can divide both sides by a non-zero number and the results will be equal. But we don't know these two things are equal. So this is an island over here. This is an island. I have to stay on my own island. I cannot move cosine to the other side, tangent to the other side. I can't bring sine to the left. But what I could do is turn everything into sines and cosines. So I get tangent becomes sine of theta on cosine of theta times a cosine of theta is supposed to equal sine of theta. Now what you would not want to do here, because the reader needs to see how we arrive at our answer, and I think we all see we're there. You wouldn't want to do something like this, where I can't really see what's going on, and then give me sine of theta equals sine of theta, and say, I got it, and I'm like, well, how did you get it? You've got this green pen all over everything. So we should, if we're going to do that, just give me something like this, where it's clear what was underneath there, and you canceled. Okay, pretty easy one. It's one of the cases we go to sine and cosine, makes things pretty simple for us. Okay, now here's what I want to talk about. You may work on this island and this island independently, but nobody's leaving their island. So I look at the side on the right, and I might want to make that sines and cosines. Cosecant, 1 on sine of theta, times secant, 1 on cosine of theta. And the side on the right. So now I start looking at just the form that we're in. And I notice here I've got a binomial. And here, or here, I've got a monomial. Things are factored, but it's a monomial. So I either want to smash the left side together or somehow break the right side apart into addition. I think I'm going to work left side here. To smash those together, I need least common denominator. It needs a factor of cosine of theta and a factor of sine of theta. What did I have to multiply this fraction by to get it on sine of theta? Or on cosine sine of theta? Well, it was on cosine of theta. I needed to multiply by sine of theta on sine of theta, giving me sine squared of theta. This fraction needed to be multiplied by cosine on cosine. So I get plus cosine squared of theta. Notice the denominators are perfect. My denominators are both sine of theta, cosine of theta. This is so good it's almost cheating. Sine of theta, cosine of theta. If the denominators are perfect, the numerators better match. And I'm like, oh, I've seen these guys together before. Maybe they just equal 1. Well, they do, in fact. There's a Pythagorean identity that says sine squared of theta plus cosine squared of theta equals 1. And we are out of this. If you ever have a doubt on an identity problem, whether you should do 2 steps in one, just don't do it. Baby steps the viewer needs to be able to follow. We can assume they have some fairly reasonable algebra skills, but they need to be able to follow your work. Use calculator to find the value to 4 decimal places. How could we possibly miss this on our calculator? You better make sure that you are set to degrees. So as I do this problem, I am punching this in my calculator as I speak. Tangent of 18.5 set in degrees is 0.3346 to 4 decimal places. And then cotangent. There's a couple ways you could miss this. One, you could have the degree symbol, or you could be working in radians. Two, we recognize our calculator doesn't have a cotangent button, but cotangent is reciprocal of tangent. And I will see people try this. They'll say, oh, then that means this should be tangent of tangent of reciprocal. They'll try something like this, set in degrees. That will not work. It's not the reciprocal of the degrees. Tangent is cotangent is the reciprocal of tangent. So I want 1 divided by tangent of 71.5 degrees. But if you are really, really perceptive, you should not be surprised when you enter that in your calculator that you end up with 0.3346 on this, approximately. That is because 18.5 and 71.5 add up to 90 degrees, and we learned earlier that the tangent of, or better yet, how about the cotangent of 90 degrees, or pi on 2, minus theta, some angle, equals the tangent of the original angle. In other words, if these guys are complementary and we're dealing with cofunctions, the results are going to be the same. So one more here we're going to take a look at. Sketch a right triangle with acute angle theta, the value theta in find the value theta in degrees and radians. This is rationalized. If I was to multiply top and bottom by root 3 on root 3, this would end up reducing to be 2 on root 3. You might see it going backwards. This is rationalized. This could be 1 on root 2. I like working with right triangles with those values. There's a good chance they're familiar triangles to us. Okay, I'm not going to try to draw this to scale. You may if you want. Theta. Cosecant, I call it the 2 a.m. wake-up call. We should know what that is in terms of x's, y's, and r's. Sine is y on r, or opposite hypotenuse. Cosecant, therefore, the reciprocal must be r on y. We want an r value of 2 when y is root 3, or a hypotenuse 2, opposite root 3, giving us the sine of 1 here. That is a very familiar triangle. This is a 30, 60, 90. If I try to draw this, if I don't draw this to scale, we may just be guessing at theta. Is it 30? Is it 60? Well, it's opposite, a bigger side than that angle is. So theta must be 60 degrees. Therefore, 1/3 of 180. Problem 2, sine. Draw the triangle. Sine y on r, or opposite on hypotenuse. Oh, that makes this a 1. That makes this a 45-45 right triangle. So this is 45 degrees, which, think about it, that is just 1, 2, 3, 4 steps to go pi. So that is pi on 4. Okay, hope that's helpful for you. Stay tuned and good luck.